Alright guys, so we're also going to do 5.6, so on the next page, just turn to that really quick. 5.6, we're going to be solving exponential functions. So, we are going to use multiple representations to model exponential functions. We actually already did that. That's what we were doing when we were going back and forth between forms. You will understand the properties of exponent expressions with positive and negative exponents. We've been talking about that. You will solve exponential functions graphically and algebraically using common bases and properties of exponents. Those common bases, that's what we're really going to be looking at. Investigate increasing and decreasing exponential functions, and we are going to model inequalities in exponential situations, and we will graph, analyze, and solve exponential functions. So, for 5.6, solving exponential functions. So, turn to page 352, so we're going to skip problem 1, and we're going to go to problem 2, okay? Here's what I want you guys to do. Partner up, so just get with the person next to you, and I want you to read the introduction, and I want you to read the little notebook page, okay? So here's what this is saying. An exponential function is a function of the form f of x equals a times b to the power of x. We've been working with these a lot, so that should be familiar looking to you. To solve an exponential function, we can use what we know about the properties of exponents and common bases. Basically, we can rewrite functions to have the same base so that we can solve them. Because if you guys take a look, let's see. What this notebook page is telling you is that in order to solve, if your variable is in the exponent, you have to get the same bases. Then you can cancel the bases and solve the exponents. We're going to do all of these problems together. So look at number 1. 3 to the power of x equals 81. Have you seen a problem so far with an x in the exponent that I have asked you to solve? Have we done this yet? No. Have you ever seen a problem with where the x is in the exponent and I have asked you to solve it? Okay, so this is what we're going to do. We need to think of what power we can raise 3 to get an answer of 81. Can I rewrite 81 using a base of 3? Yes. 81 is 3 to the what power? 4. 3 to the 4th. So here's how you're going to show your work. 3 to the x, that's the left-hand side, equals 81 is the same as 3 to the 4th power, correct? So all I did was rewrite 81 using a base of 3. Now, let's see if this makes sense. If 3 to the x power is equal to 3 to the 4th power, what does x have to equal? 4. Here's how you can show your work. We can, after you get the same bases, you can drop them, and we set the exponents equal to each other. So in this case, x equals 4, and that's your answer. There will be other problems where more work is in, but that's the basic. Okay? I know this is different, so just bear with me. Look at number 2. 2 to the 4x power equals 1. Let me zoom in a little bit. Oh, there, that's better. 2 to the 4x equals 1. Okay. Can I rewrite 1 as a base of 2? Yeah. Anything to what power gives you a 1? What power gives you a 1? 0. So do you guys agree that this is the same as 2 to the 4x, that left side didn't change, equals 2 to the 0 power? 2 to the 0 power is 1? Do I have same bases now? Yes. So drop the bases, and we are left with 4x equals 0. So you set the exponents equal to each other. So your steps are you get the same base, drop the bases, solve the exponents. So how would I solve for x in this case, guys? What would you do next? 4x equals 0. Divide by 4. And 0 divided by 4 gives me 0. So x equals 0. Okay. Question so far. Alright, number 3. 4 to the 8 minus x equals 1 over 64. Can I rewrite 64 so that it is a base of 4? Yeah, 64 is 4 to the what? 4 to the third. So let's rewrite this. 4 to the 8 minus x equals 1 over 4 to the third power. You have to keep it as a fraction for right now. Now, do I have the same bases yet? I say no. Can anybody tell me why they think it's no? Brittany. Numerator, close. My 4 to the third power is in the denominator right now. Where is the 4 on the left-hand side? Can I move 4 to the third to the numerator? Yes, but I have to do what? Make it negative. So you can move it, but we have to make it negative. So let's rewrite this. 4 to the 8 minus x equals 4 to the negative 3. Now can I drop the bases? Yes, so drop the bases, and that gives you 8 minus x equals negative 3. But I need to solve for x, so what would you guys do next? Add what?
Add 8.
If I add 8, does that cancel out? This is a positive 8, so what do I have to do? Subtract it. Because 8 minus 8 gives me 0. So that leaves me with, I'm going to go over here, negative x equals what? Negative 11. Now, I don't want negative in my x, so if negative x equals negative 11, what does x equal? Positive 11. Okay. After we get the same bases, it's not hard. It's just getting the base. Okay, so let's look at number 4. 5 to the 9x equals 5. Do I have the same base? Yes. What's the exponent of this guy? A 1. So why don't you just write the 1 in there for right now? Now I have the same bases, so drop them, and we get 9x equals what? Equals 1. So what would you do to solve for x? Divide by 9. So what do we get in this case? X equals 1 over 9. Not too bad? Okay, so number 5. 1 over 3 to the x plus 5 equals 243. What's the base that I'm going to try and get? First of all, 3. So can we write 243 as a base of 3?
Yes.
Okay, so find it. Figure out what it is. Okay, so on the left-hand side, I'm not going to change anything yet. I have 1 over 3 to the x plus 5. 243 is 3 to the what? 3 to the... I heard one person get it. Who else? 243 is 3 to the 5th power. Okay. Do I have same bases yet? No, this is a base of 3, and this guy has 3 in the denominator. Can I move 3 to the numerator? Yes, but what do I have to do to the exponent? Make it negative. So this is how you are going to write it. 3, negative, and then in parentheses, x plus 5. Because it's the whole exponent that's becoming negative, not just the x. So put it in parentheses for now. Equals 3 to the 5th. Guys, what would my next step be? Drop the bases. So we would be left with negative x plus 5 equals 5, and I want you to finish solving that one. Okay, guys, who wants to give me my first step? Anthony. What would you do first? Can I subtract 5 from each side yet?
No.
A couple people say no. What do I have to do before I can do that, Dana?
You have to distribute the negative.
Exactly, I have to distribute the negative first. So that's going to give me negative x minus 5 equals 5. And Anthony, then what do I do?
Then you add 5.
Then I add 5 to both sides. So I get, and I have to move off to the side, guys, negative x equals what? 10, but I don't want a negative in my x. So if negative x equals positive 10, that means positive x equals negative 10. Okay? One more and then I think we're good. And every single one of these, every single one that you will see on your homework are like these. Okay, I have 2 to the negative x equals 1 over 2. Do I have the same base?
Yes.
Almost, not quite. What do I have to do? I have to move the 2 up. If I move the 2 up, what does that make my exponent? It doesn't change the value of the number, it changes the value of the exponent. So the 2 stays positive, but the exponent becomes negative 1. Okay? Alright, everybody, what would my next step be? Drop the bases, and we get negative x equals negative 1. So what does positive x equal? Positive 1. So anytime you have a fraction, move it and make the exponent negative, and then you can drop your bases. Does this make more sense? Does it help? Excellent. Okay. Last thing we're going to do is problem number 3, which is a word problem. So bear with me, okay? Let's look at problem 3. I'll read it for you. How about that? I know that you guys are mentally exhausted from a week-long break, so I will read it to you. Just read along. Okay, problem 3 is all about inverses, which you do need to know. So, the amazing Aloysius, I think, did I say that right? Is practicing one of his tricks. I think we did a problem with him already. He's the magician kid, right? As part of the trick, he cuts the rope into many pieces and then magically puts the pieces of rope back together. I think we read about this exact same trick. He begins the trick with a 10-foot rope, so will you guys underline 10-foot rope just so you know how long it starts out with? And then cuts it in half. He takes one of the halves and cuts that piece in half. He keeps cutting the pieces in half until he is left with a piece so small that he can't cut it anymore. Part A wants us to complete the table to show the length of rope after each of Aloysius' cuts, write each length as a whole number, mixed number, or fraction, and then graph the points from the table. Okay? So, the rope is 10 feet long, so when he makes 0 cuts, his rope is still 10 feet, right? When he cuts that in half, so he makes 1 cut, what is the length of the rope? 5. Let's start graphing as we go. So 0, 10. So the number of cuts is 0, and the length of the rope is 10. So our first point is going to be right there. I think it's easier to graph as we go. When he makes 1 cut, so number of cuts is 1, the length of the rope was 5, so put a point there. So then he takes that 5-foot piece, and then he cuts that in half. So he made 2 cuts. What is the length of the rope now? 2.5. It says whole number, mixed number, or fraction. So not 2.5, it's going to be 2.5, right? So when he makes 2 cuts, the length of his rope is 2.5. What about when he cuts a 2.5-foot rope in half? What is he left with? 1 1/4. So half of 2 is 1, half of a half is a fourth. So when he makes 3 cuts, he's at 1 1/4, so that's like right here. What about when he makes 4 cuts? So, here's what I'm going to do to make this a little bit easier. Let's rewrite 1 1/4 into a mixed number. 1 times 4 gives me 4, plus 1 gives me 5. So he's taking 5/4 and he's cutting that in half. So I'm going to show my work on this one just so that you guys can see what we're doing. So he had a 5/4 and he cut it into 1/2. So we're multiplying by 1/2. What does that leave you with? 5 what? 8. So when he makes 4 cuts, his rope is going to be 5/8, which is just over half of a foot. Would it make sense to connect all of our points?
No.
Why not?
Because they're different.
What type of graph is this? Continuous or discrete? Discrete, because we're only making 1 cut, 2 cut, 3 cuts, right? We're not doing 1 1/2 cuts. We're not doing 2 1/2 cuts. So we leave all of our points as discrete. So we're going to leave this blank for right now. And then let's look. This function family is what? What type of function is this? Function families are linear, quadratic, exponential, or what was the other one? Piecewise, linear piecewise. Which one is this? Exponential. So this is an exponential function. And we want to write the length of a rope as a function of the cut. So, this is our basic exponential function. Y equals AB to the power of X. You guys read that at the front of problem 2. Okay, so at problem 2, it told you that the standard form of a function was A times B to the X power. So that's all we did right here. Y equals AB to the X. A is your initial length. What's the initial length in this problem? 10. We don't know what B is. That's what we're going to solve for. Do I have an X and a Y that I could plug in?
Yes.
Yeah, I actually have a whole bunch of them. Which X and Y do you think would be easier to plug in?
5.
Yeah.
What about 0 and 10?
Oh.
Or 1 and 5, it doesn't really matter. So why don't we use 1 and 5? That might be easier. So this is going to be Y is 5 and X is 1. That's actually going to make it easier for us. So how would I solve this? B to the first power is what? B. So this is 5 equals 10B, and then what would you do? Divide by 10. So B equals what? 5/10, which is 1/2. So how do I use this to write a function? Did they tell us what our variable was? C. Okay. So f of c, now we can use it as a function, equals, my starting was 10. A is always your starting number. But B is what? 1/2. And all of that is being raised to the power of, we're going to change X to C though, right? Okay. Now, yeah, that's good. Okay?